Most of them say the universe is about 13 billion years old. What if it's not?
Something is wrong. We may have to revise our theory of the creation of the universe.
With a groundbreaking discovery from the James Webb Telescope, we are on the brink of a revolution in space science. One of the oldest galaxies ever seen has challenged every theory of time and space we have long believed. Michio Kaku, the renowned physicist, claims that time doesn't exist as we once thought. So, what is really happening in this vast universe? Get ready to explore the mysteries that James Webb has uncovered. Recently, the telescope's observations once again entered the first 500 million years after the Big Bang, and this time it observed galaxies that are most definitely anything but infantile, as in they are extremely massive and mature, more than previously expected for such early times. And now astronomers are staring at a galaxy that could be one of the oldest ever, and the shocking part is that it already contains billions of stars. Interestingly, only 2 years ago, the Hubble Space Telescope spotted this cosmic giant as an unusual point of light in its field of view. Scientists couldn't have imagined that this odd speck of light is a monstrous galaxy lurking at the edge of time until they turned Webb to look at it. Webb's observation revealed that the point of light is actually a primordial galaxy that is far more massive and mature than it should be. Dubbed GZ9P3, this galaxy is at a redshift of Z equal 9.3, which means we are seeing it as it was only 510 million years after the Big Bang. Now, we have spotted other galaxies as they were around 3,500 million years after the Big Bang, but none of them are as massive as this one. Together, these findings imply that stars within the galaxy must have formed more rapidly and effectively than previously believed in order for the galaxy to attain its current size. But that's not all. GZ9P3 also has a strange shape that might be giving away the early universe's secrets. The team behind the discovery found that the galaxy has 2 bright patches within it, revealing its 2 dense nuclei. This most definitely points towards a galactic merger. 2 primordial galaxies smashing together in the infant universe. What's more, the team not only identified the age, mass, and shape of this ancient galaxy, but also zoomed into its stellar population and found that young, bright stars dominate the galaxy's image. The study team used the JWST to find specific elements like silicon, carbon, and iron in the older stars of GZ9P3. Iron is the heaviest element stars can make. When these stars exploded, they spread these elements into space, enriching the early universe with metals that later became part of new stars. They also found that there were more old stars in GZ9P3 than they thought. This suggests that galaxies may have become chemically mature quicker than we thought, with stars enriching the universe with metals faster than expected. The unexpectedly mature, older population of stars in GZ9P3 challenges our current understanding, suggesting that stars formed much earlier than previously thought to have aged sufficiently by this cosmic time. These findings imply that a new model may be required to explain the rapid growth of galaxies to such a chemically mature state in addition to their surprising size. They also imply that galactic mergers may have dominated the universe immediately after the Big Bang. Our current cosmological framework may not be incorrect, but our perception of the rapidity of galaxy formation likely needs adjustment, given that these galaxies are more massive than previously deemed feasible. If you found this video interesting, don't forget to hit like and subscribe to the channel so you won't miss the next mysterious discoveries about the universe. Join us as we continue our journey to unravel the great mysteries of the infinite cosmos. Back in 2014, scientists began to notice something odd. Galaxies with redshifts up to 5 seemed to behave as if the universe wasn't expanding. Hubble Space Telescope images supported this idea, showing galaxies that appeared the same size regardless of distance. Now, with the James Webb Space Telescope, JWST, taking center stage, the mystery has only deepened. JWST continues this trend even for galaxies with redshifts as high as 12, making astronomers question everything they know about the expanding universe theory. Simply put, JWST's observations suggest that these distant galaxies aren't shrinking as they should if the universe is expanding. It's as if the redshift is simply a function of distance, not expansion. This leaves scientists with a mind-boggling conundrum. For the expanding universe theory to hold, these galaxies must be unimaginably small, like a grain of sand shining as bright as a spotlight. But that's not the case. Take GHZ2, for example, a galaxy spotted by JWST. It's far brighter than the Milky Way, yet it's a mere 300 light-years in radius, compared to the Milky Way's 50,000 light-years. Its brightness per unit area is 600 times greater than any galaxy in our local universe, and its density is tens of thousands of times higher than nearby galaxies. The size and smoothness of these galaxies challenge the very foundations of the Big Bang theory. For years, Hubble images have been difficult for astronomers to explain. The dense, powerful galaxies they observed resembled something out of a cartoon, presenting a puzzle that just didn't fit the accepted models. Now with JWST, that puzzle has become even more complex. Theorists have proposed that these small galaxies could have merged over billions of years, colliding like tiny toy cars until they formed the full-sized galaxies we see today. But here's the twist. JWST has revealed no signs of such cosmic collisions. These galaxies remain pristine, smooth spirals with no evidence of galactic fender benders. A recent study, aptly titled Panic, shows that there are 10 times more of these pristine galaxies than predicted. It's like finding a highway full of speeding cars, but no accidents. This is a serious blow to the idea of galaxy mergers. Without signs of these galactic crashes, the notion that small galaxies grew into larger ones collapses. If these galaxies didn't grow in size, they weren't small to begin with. Consequently, the expected optical illusion from an expanding universe doesn't exist. This revelation shakes the foundation of the Big Bang theory, leaving scientists questioning whether the universe is expanding at all. If it isn't, the Big Bang theory might face its biggest challenge yet. Let's delve deeper into an aspect that could turn the entire Big Bang theory on its head. According to the Big Bang theory, everything in the universe was created following a colossal explosion. But what if that isn't true? What if some of the galaxies we are now observing existed before the Big Bang? If this were the case, it would radically shift our understanding of the origins of the universe, challenging one of the most established theories in modern science. The colors that JWST captures aren't just stunning, they tell a much deeper story. The color of a star can reveal its age. Young stars burn with a bright blue light, while older stars, like our own sun, emit a more subdued yellow or red glow. By analyzing these colors, astronomers can estimate the age of the stars in these ancient galaxies. Here's where the problem arises. According to the Big Bang theory, the galaxies farthest away, the ones JWST is capturing, should be from a time around 400 to 500 million years after the universe was born. But some of these galaxies appear to contain stars that are over 1 billion years old. This creates a serious issue because, according to the theory, nothing should be older than the Big Bang itself. Another major expectation of the Big Bang theory is that as we look farther back in time, we should see fewer galaxies, eventually reaching a cosmic dark age where no galaxies existed yet. However, JWST's images tell a different story. Galaxies as large as the Milky Way seem to have been common, even just a few 100 million years after the supposed Big Bang. In fact, the new data suggests there are at least 100,000 times more galaxies at high redshifts, above 10, than predicted. This leads to the obvious question: how could so many massive galaxies form so quickly? The short answer is, they likely couldn't, not under the traditional Big Bang model. This is why these new discoveries are shaking the foundations of our understanding of the universe. But it gets even more complicated. Recent research suggests that the Big Bang theory is off the mark in numerous areas. Believe it or not, the theory has been found to be wrong in 16 different predictions. That's right, 16. The only prediction that has held up is the abundance of deuterium, a specific form of hydrogen. But even this isn't enough to save the theory from its other significant flaws. For instance, the Big Bang theory predicts double the amount of helium and 20 times the amount of lithium that we actually observe in the universe. It also struggles to explain the existence of the massive structures we see today. According to the theory, these gigantic formations simply don't have enough time to have evolved since the universe began. And then there's the issue of predicting the density of matter in the universe, a task the Big Bang theory also falls short on. And let's not forget those supposed asymmetries in the cosmic microwave background, the remnants of the early universe's radiation. The Big Bang theory originally claimed they didn't exist, but now we know they do. It's like the universe is pulling a cosmic plot twist, making us rethink everything we thought we knew. In light of these new observations and data, it's clear that our current understanding of the universe's origins may need to be revisited. The Big Bang theory, once considered unshakable, is now being questioned in ways that could lead to a revolutionary new view of the cosmos. There's a new crisis brewing in the cosmos, one that's shaking the foundations of our understanding of the universe. For years, scientists have relied on the Big Bang theory to explain how everything came into existence. But a recent discovery has called this widely accepted theory into question. And it's not just one crisis. A fresh cosmological distress is emerging that's challenging our models in ways we've never seen before. I've spent my entire life developing a particular theory of the universe, and now that theory is being questioned. And you know what? I welcome it. This is how we progress in science, by confronting challenges and evolving our understanding. If you've ever looked up at the night sky, away from city lights, you've probably been mesmerized by the stars. You might have even seen the Andromeda Galaxy as a faint smudge among the stars. The universe is vast and filled with galaxies, but the question remains, how much of the universe do they fill? More importantly, how much matter is actually there? It seems like a simple question, but the answer is anything but. In fact, this dilemma has created a new problem in cosmology, known as the S8 tension. This tension is a mysterious new issue that has scientists scratching there. The second method is based on cosmic microwave background measurements from the standard model of cosmology. Here's the problem. The S8 value derived from this model doesn't match the values obtained from low redshift observations. This discrepancy lies at the heart of the S8 tension. Despite the countless theories and observations we have, there's clearly something we're missing. Something isn't adding up. What's going on? In an effort to resolve this, astronomers turned to one of the most powerful supercomputers in the world. They carried out the largest cosmological simulations ever attempted, using more than 50 million hours of computing time spread across 30,000 processors. This ambitious project, called Flamingo, full hydro large-scale structure simulations with all sky mapping for the interpretation of next-generation observations, aim to better understand how matter is distributed in the universe. Unlike earlier simulations, which focused mostly on dark matter, Flamingo took things to the next level. It didn't just simulate dark matter, which makes up most of the universe's mass, but also accounted for normal baryonic matter, ordinary matter like stars, planets, and everything else we can see. Even though baryonic matter is only 1/5 of the total mass in the universe, it still plays a significant role, especially at small distances. For example, supermassive black holes and supernova explosions can impact the growth of galaxies. While Flamingo made significant strides, like accurately simulating the formation of the Milky Way and the Andromeda Galaxy, it ultimately fell short of resolving the S8 tension. The simulation couldn't explain the weaker-than-expected clumping of matter in the present-day universe. In fact, the results of Flamingo may even suggest that there's something fundamentally wrong with our standard model of cosmology. To make matters more complicated, the Flamingo simulation contradicts the observations made by the James Webb Space Telescope and other observatories regarding the distribution of matter. According to our current theories, galaxies should be clustered 7% more tightly than what we observe. Even with Flamingo's advanced calculations, which include the effects of supermassive black holes, the clumping was still off by 5%. Adding fuel to the fire, Webb's observations have also confirmed the existence of the so-called Hubble tension. This tension refers to the discrepancy in measurements of the universe's expansion rate, known as the Hubble constant. The Hubble Space Telescope first noticed this inconsistency, but now Webb has validated it. The universe's expansion rate simply doesn't align with our current models. With measurement errors ruled out, the only conclusion left is both intriguing and exhilarating. We may have misunderstood the very nature of the universe. New theories are already emerging, with some scientists even suggesting that we need to rethink the role of dark matter altogether. Could it be that dark matter isn't as crucial as we once thought? Or perhaps the universe operates on entirely different principles than we've ever imagined? Let us ask you this. Have you ever wondered if time as we understand it actually exists? Or is it just a human-made concept to help us separate the past from the now? We know it's a heavy question to ask, but stick with us. There's a theory that suggests that time is an illusion crafted from our human memories. This theory proposes that everything that ever happened or will happen is happening right now. It's a little strange, isn't it? Let's dig deeper into this. You'd think, naturally, time flows forward, right? But guess what? The laws of physics don't actually demand that. These laws work just as well whether time is moving forward or backward. If you've heard of the Big Crunch theory, it suggests that when the universe finishes expanding and begins to contract, time might start to run backward. And as the universe shrinks, it'll get hotter, sort of a Big Bang in reverse. You might wonder, what comes after the Big Crunch? It's a question that has puzzled us all. Some theories suggest that a new universe may emerge from a fresh Big Bang, while others propose that our universe might reappear somewhere else entirely, like a cosmic bubble popping into existence. There are even theories suggesting that this cycle might repeat itself over and over, leading to countless universes. The notion that time could move both forward and backward has led some scientists to a radical conclusion. Time, as we know it, may simply be a human invention. These scientists propose that we live in what's known as a block universe, where space and time are intertwined, an idea grounded in Einstein's theory of relativity. In this model, every event, whether it's in the past, present, or future, occupies its own specific location within the four-dimensional fabric of space-time. What does this mean for us? It suggests that every moment, whether already lived or yet to happen, continues to exist somewhere in space-time, just as tangible as the present. MIT physicist Max Tegmark illustrated this mind-bending idea with a simple yet profound analogy. He explained that we can perceive our reality either as a three-dimensional world where things happen over time, or as a four-dimensional realm where nothing truly happens because everything simply is. If the latter is true, then time may be nothing more than an illusion, a trick of perception. In this view, the past, present, and future are all equally real, always existing, unchanged and unchanging. It's a concept that's difficult to fully grasp, but is undeniably fascinating, offering a glimpse into the mysterious and magical nature of our universe. Adding to this discourse is British physicist Julian Barbour, who offers a different perspective on time. Barbour envisions reality as a series of discrete now moments, much like flipping through the individual photos of a photo album. Each snapshot represents a unique moment in time, existing in isolation from the others. According to Barber, the past is merely a construct of our brain's memory. We only feel as though we have a past because we recall it. In his view, the concept of a continuous past may be an illusion. Barber's theory is further expanded through his concept of Plutonia, a vast landscape where each moment exists as a separate point in space. These points follow precise mathematical rules, making time itself irrelevant within this framework. This intriguing idea loops back to Albert Einstein, whose theory of space-time remains central to modern physics. Yet even Einstein's revolutionary work has sparked new questions. What if his concept of space-time is flawed? What if, by discarding it altogether, we could unlock a clearer understanding of the cosmos? Though these ideas may seem jarring, they highlight an essential truth about science. It thrives on questioning established beliefs. Throughout history, scientific progress has been driven by bold ideas and paradigm shifts. For instance, for over 1,000 years, the geocentric model dominated our understanding of the cosmos, positioning Earth as the center of the universe. Then, Nicolaus Copernicus came along with a revolutionary proposal. Earth is just another planet, orbiting the sun. This radical shift overturned centuries of accepted wisdom. Following Copernicus, Isaac Newton introduced a new framework for understanding the universe: gravity. Newton posited that all objects with mass exert an attractive force on one another. This gravitational pull explained why the Earth orbits the sun and why the moon orbits the Earth. Newton's ideas shaped our understanding of the universe for nearly 300 years, but even Newton's theory had its limits. In 1915, Albert Einstein expanded on these ideas with his general theory of relativity. Einstein suggested that massive objects like the sun warp the fabric of space-time itself, causing other objects to follow curved paths, what we perceive as gravitational attraction. This marked another revolution in our understanding of the universe, challenging the long-held notions established by Newton. The lesson? Science is never static. It evolves, shaped by new discoveries and daring ideas that push the boundaries of our understanding. As we continue to explore the mysteries of time, space, and the universe, we may be on the verge of yet another revolutionary leap. The progression from the geocentric model to Copernican heliocentrism and from Newton's laws of gravity to Einstein's theory of general relativity underscores the ever-evolving nature of science. Despite the strength of Einstein's theories today, physicists continue to probe the boundaries of our understanding, especially when it comes to time and space. Einstein's space-time theory has stood the test of time for over a century, with its most significant validation arriving in 2015 with the detection of gravitational waves. However, no scientific theory is beyond question. A challenge arises when Einstein's general relativity, which describes the smooth fabric of space-time, encounters the unpredictable world of quantum physics. In the quantum realm, particles defy logic, existing in two places simultaneously. Schrödinger's famous thought experiment, where a cat is both alive and dead until observed, illustrates this paradox. This quirk of quantum mechanics seems irreconcilable with Einstein's vision. As Sabine Hossenfelder points out, a gravitational field cannot be in two places at once, as Einstein's theory demands, yet quantum physics suggests otherwise. The clash between these two pillars of modern physics has spurred a search for a theory that unifies them, leading to exotic ideas like string theory, which posits that all particles are tiny vibrating strings resonating across 11 dimensions. But this elegant theory remains speculative, as no experimental proof of these extra dimensions has yet been found. Spurred by concerns over string theory's complexities, some physicists have pursued an alternative approach called loop quantum gravity, LQG. This theory seeks to reconcile the conflicting theories of general relativity and quantum mechanics by rethinking a fundamental premise of general relativity, that space-time is smooth and continuous. Instead, LQG posits that space-time is composed of tiny loops, suggesting a woven structure at the most minuscule scales. Imagine a cloth. From afar, it appears smooth, but up close, you see it's made of interwoven threads. Similarly, zoom into a digital photo, and you'll find it's composed of individual pixels. The challenge of LQG lies in the scale where these loops become noticeable. The Planck scale, an unimaginably small distance, about a trillionth of a trillionth of a trillionth of a meter. At this scale, there are more loops in a cubic centimeter of space than cubic centimeters in the observable universe. Proving this theory with current technology is near impossible. To test LQG, we'd need a particle accelerator 1,000 trillion times more powerful than CERN's Large Hadron Collider, a machine the size of our Milky Way galaxy, an impossibility with today's tools. While such an enormous accelerator is unfeasible, physicists from the UK, France, and Hong Kong have proposed an alternative. They're experimenting with an incredibly cold gas of cesium atoms, known as a Bose-Einstein condensate, to explore whether gravity has a quantum nature. Alternatively, the universe itself may offer clues. Light from distant galaxies has traveled billions of light years across space-time. If space-time contains tiny defects, light could interact with them along the way. While each interaction would be minuscule, over vast distances, they could add up, leaving detectable distortions. Astronomers have spent the past decade investigating these distortions using light from distant gamma-ray bursts, the intense flashes of light created by massive stars collapsing at the end of their lives. Interestingly, a consistent distortion in the gamma-ray bursts spectrum has emerged, but its origin remains mysterious. Sabine Hossenfelder noted that it's unclear whether this distortion happens during the light's long journey or at the burst's source. To truly unravel this mystery, we might need to rethink Einstein's concept of a smooth space-time. Einstein viewed space-time as a stage, a backdrop upon which the universe's events unfold. But as we dive deeper into quantum gravity, we may need to reshape this understanding, altering not just the play, but the stage itself. 3 pioneering physicists, Laurent Friedel, Robert Lee, and George Harnick, are pushing this boundary further. They propose that our conventional thinking about space-time may be constraining our understanding. In their view, space-time isn't a separate entity from the objects within it. Rather, it emerges from the interactions between those objects. This revolutionary idea flips the script, suggesting that space-time isn't something to be reconciled with the quantum world. It originates from it. This new perspective on space-time theory offers a radical shift that may unlock one of the most perplexing puzzles in physics, the entanglement phenomenon. In this mysterious quantum scenario, 2 particles are so deeply connected that a change in one instantly affects the other, regardless of the distance between them. This seems to defy Einstein's relativity, where nothing can travel faster than light. Einstein himself was so troubled by this concept that he famously called it spooky action at a distance. However, through the lens of modulus theory, this paradox begins to make sense. If space-time emerges from the quantum realm, then quantum closeness may trump physical distance. As George Harnick described, it's akin to feeling closer to a loved one far away than to a stranger next door. In the quantum world, such non-local connections make perfect sense. For the last 5 years, Friedel, Lee, and Harnick have been developing this groundbreaking idea, cautiously optimistic about its potential. Their approach envisions a quantum world that naturally includes gravity, instead of forcing quantum rules onto gravity as loop quantum gravity does. Their next challenge? Integrating time into this model. Though abstract, the implications are profound. Our understanding of space-time shapes how we comprehend gravity and quantum physics. A clearer grasp of the quantum structure of space-time could revolutionize technology, paving the way for future innovations. The reigning theory of space-time, much like a long-established ruler, may soon face competition from these fresh ideas. While it's uncertain which theory will ultimately prevail, the revolution could usher in a new era of discovery in theoretical physics. Stay informed, stay curious, and together, let's explore the truths that matter. Don't forget to hit the notification bell so you never miss an update. Thank you for watching our video. The James Webb Space Telescope is the most significant advancement in human endeavor toward unraveling the mystery of the cosmos. More than just a telescope, James Webb is humanity's most potent eye in the sky, providing the ability to observe the universe billions of years back and hopefully unlock the key to the cosmos's evolution and provide answers to some of the most fundamental questions asked by humanity. But when James Webb used its powerful and sensitive infrared eye to peer back into the beginning of times, what it unveiled was nothing short of revolutionary and potentially catastrophic for our understanding of the cosmos. The revelations James Webb brought forth would set the scientific community on edge, igniting fierce debates and existential questions about the very fabric of our universe.
Thing is wrong. We may have to revise our theory of the creation of the universe.
Join us as we dig deep into what James Webb really saw at the dawn of time. To understand what James Webb is seeing, we first need to revisit the concept of the beginning of time as described by the Big Bang theory. According to this theory, the universe began as an extremely hot and dense point, often referred to as a singularity, approximately 13.8 billion years ago. This singularity contained all the mass and energy of the universe in an infinitesimally small space, and for reasons still not fully understood, it began to expand. This expansion marked the birth of the universe, as space itself began to stretch, and time as we know it began to flow. In the first fractions of a second after the Big Bang, the universe underwent a rapid expansion known as cosmic inflation. During this brief period, the universe expanded exponentially, smoothing out any irregularities and setting the stage for the formation of galaxies and large-scale structures. As the universe continued to expand and cool, energy was converted into matter through processes described by quantum mechanics and Einstein's theory of relativity. In the first few minutes after the Big Bang, conditions were right for the formation of simple atomic nuclei, primarily hydrogen and helium, in a process known as nucleosynthesis. These elements would later serve as the building blocks for stars and galaxies. As the universe expanded and cooled further, gravity began to take over, pulling matter together to form the first structures in the universe. Small density fluctuations in the early universe, amplified by gravity, led to the formation of dark matter halos, within which gas could cool and condense to form stars. These early stars, known as population 3 stars, were massive and short-lived, playing a crucial role in enriching the universe with heavier elements through supernova explosions. Over time, these stars began to cluster together under the influence of gravity, forming the first galaxies. Galaxies are the basic building blocks of the universe, vast systems containing billions of stars along with gas, dust, and dark matter. The formation of galaxies was a key step in the universe's evolution, as they provided the environments in which stars could form, evolve, and die, creating the complex chemical elements needed for planets and life. In the centers of galaxies, clouds of gas and dust collapsed under gravity to form stars. Around some of these stars, the remaining gas and dust coalesced to form planets. Our own solar system, for example, formed about 4.6 billion years ago from a cloud of gas and dust left over from previous generations of stars. The sun formed at the center of this cloud, with the remaining material forming the planets, moons, asteroids, and comets that make up our solar system. But while most of us strongly believe that the Big Bang is the best way to explain how the universe started and how it changed over time, The fact is that this model, while powerful, does not provide a complete account of cosmic history. Instead, it leaves unanswered questions about the nature of dark matter and dark energy, the asymmetry between matter and antimatter, and critically, the details of the universe's dark ages, the period after the Big Bang, but before the first stars ignited. One of the most significant gaps in the Big Bang theory involves the formation of the first stars, known as population 3 stars. The formation of the first stars marks one of the most significant epochs in cosmic history, the transition from the dark ages to a universe filled with light and structure. This event, known as cosmic dawn, is shrouded in mystery, primarily because the first stars are thought to be fundamentally different from the stars we observe today. The first stars formed from the primordial hydrogen and helium gas left over from the Big Bang. Unlike stars today, which form in regions enriched with heavier elements, metals, the first stars were born in an environment devoid of such elements. This absence of metals profoundly affected their formation and characteristics. One of the central mysteries surrounding the first stars is their mass. Theoretical models suggest that, in the absence of metals, the cooling processes in the early universe were inefficient, leading to the formation of extremely massive stars, with masses ranging from tens to hundreds of times the mass of the Sun. These massive stars would have had short lifetimes, burning through their nuclear fuel rapidly and ending their lives in violent supernovae or collapsing directly into black holes. Despite their importance in cosmic history, detecting the first stars has proven to be a formidable challenge. These stars formed at such an early epoch that they are extremely distant, and their light has been redshifted to wavelengths that are challenging to observe with current technology. Moreover, because they were so massive and short-lived, they would have rapidly ended their lives in powerful supernova explosions, leaving behind little direct evidence. One of the key challenges in detecting population 3 stars is the sheer distance involved. The light from these stars has traveled for over 13 billion years to reach us, and during that time, the universe has expanded, stretching the light into the infrared part of the spectrum. This means that traditional optical telescopes, like the Hubble Space Telescope, are not well suited for detecting them. However, the advent of the James Webb Space Telescope has provided a new window into this distant past. As the most powerful space telescope ever built, James Webb is equipped with a suite of advanced instruments optimized for infrared observations. This capability is crucial for studying the early universe, where the light from distant galaxies and stars has been stretched into the infrared part of the spectrum due to the universe's expansion. James Webb's design also allows it to peer through dust clouds that obscure many regions of space from visible light telescopes like Hubble. This is particularly important for studying the early stages of star and galaxy formation, as these processes are often shrouded in dense clouds of gas and dust. That's why one of James Webb's primary science goals is to observe the first galaxies and stars, probing the epoch of Rhionization and beyond. By capturing light from objects that formed just a few 100 million years after the Big Bang, the telescope can provide direct evidence of the universe's earliest structures. This, in turn, will help answer fundamental questions about how the first stars formed, how they influenced their surroundings, and how they led to the complex cosmic web of galaxies we see today. And as expected, since its launch, James Webb has already begun to revolutionize our understanding of the early universe. One of its most significant achievements has been the discovery of the earliest galaxy ever seen. Named JADES GS Z14-0, the galaxy formed at least 290 million years after the Big Bang, and contains stars that have been bursting into life since an estimated 200 million years after our universe began. Spotted by James Webb's Near-Infrared Spectrograph, or NIRSPEC instrument, the mysterious origins and rapid development of the stars has opened up some fundamental questions about how our universe came to be. Astronomers aren't certain when the very first globules of stars began to clump into the galaxies we see today, but cosmologists previously estimated that the process began slowly within the first few 100 million years after the Big Bang. Current theories suggest that halos of dark matter, a mysterious and invisible substance believed to make up 85% of the total matter in the universe, combined with gas to form the first seedlings of galaxies. 1 billion to 2 billion years into the universe's life, these early proto-galaxies reached adolescence, forming into dwarf galaxies that began devouring one another to grow into ones like our own. But discoveries made by James Webb confounded this view. In February 2023, a group of astronomers analyzing data from the telescope discovered a group of 6 gargantuan galaxies aged between 500 to 700 million years after the Big Bang, that were so massive they were in tension with 99% of cosmological models. The light from JD's GS Z14-0 is similarly puzzling. In the new research, the light detected by NER SPEC finds its origins in an enormous halo of young stars surrounding the galaxy's core, which have been burning for at least 90 million years before the point of its observation. The galaxy is also crammed with unusually high quantities of dust and oxygen, which suggests its history of star birth and death may be even longer. Interestingly, this finding shows that ultra-bright galaxies in the early universe are not just the product of active black holes greedily gobbling up matter, as is often assumed to be the case. The new observations show that runaway star formation is also a viable explanation for the surprising brightness of these ancient galaxies. So how did galaxies like Jade's GS Z14-0 produce so many stars so quickly? Answers to this cosmic mystery remain elusive, but it's unlikely they will break our current understanding of cosmology. Instead, astronomers are toying with explanations that include the earlier-than-anticipated appearance of giant black holes, supernova feedback, or even dark energy to understand why these ancient stars were able to form so rapidly. Fascinatingly, in addition to discovering early galaxies, James Webb has provided critical insights into the formation of the first stars, known as population 3 stars. While direct observation of the very first stars remains elusive, James Webb has detected signatures of their presence through the observation of early galaxies. The ultraviolet light emitted by these stars ionized the surrounding hydrogen gas, contributing to the reionization of the universe. By studying the spectra of these galaxies, the telescope has identified the chemical fingerprints of the first stars, providing evidence that these primordial objects played a significant role in shaping the early universe. Webb's observations have also hinted at the possible existence of population 3 star clusters, which would be some of the oldest and most massive star-forming regions ever observed. These clusters would have been responsible for producing the first heavy elements in the universe, setting the stage for the formation of later generations of stars and galaxies. Another area where the Webb telescope has made groundbreaking discoveries is in the study of black holes during the cosmic dawn. Supermassive black holes, with masses millions to billions of times that of the Sun, are known to exist at the centers of many galaxies. However, their origins and how they grew so massive in such a short period after the Big Bang have been long-standing mysteries. James Webb has detected signs of supermassive black holes in some of the earliest galaxies, providing clues about their formation. One theory is that these black holes formed from the collapse of massive primordial stars or dense star clusters, which then rapidly accreted gas and merged with other black holes to grow in size. The presence of these black holes in early galaxies also has implications for galaxy formation. It suggests that black holes and galaxies may have grown together, influencing each other's evolution. The intense radiation and outflows from these black holes could have regulated star formation in their host galaxies, shaping the development of cosmic structures. Moreover, data obtained by James Webb also have provided valuable data on when and how reionization occurred. By observing the light from distant galaxies and quasars, James Webb has measured the amount of neutral hydrogen in the early universe, offering insights into the timing and duration of reionization. Interestingly, Webb's findings suggest that reionization may have been a more complex and extended process than previously thought. Rather than occurring rapidly over a short period, reionization might have proceeded in stages, with different regions of the universe being ionized at different times. This challenges the traditional view of a uniform, simultaneous reionization and opens up new avenues for research into the interactions between early galaxies, black holes, and the intergalactic medium. What's notable, the insights provided by James Webb are not just of interest to astronomers. They have broader implications for our understanding of the Big Bang theory itself. By providing a clearer picture of the universe's first billion years, James Webb helps fill in critical gaps in our knowledge, offering new data that can be used to refine and test cosmological models. For instance, Webb's observations of early star and galaxy formation challenge existing models of how quickly structure formed in the universe. If star formation began earlier than expected, this could have implications for our understanding of dark matter and its role in cosmic evolution. Similarly, the detection of heavy elements in early galaxies suggests that the first stars may have been more massive and short-lived than previously thought, potentially influencing models of stellar evolution and nucleosynthesis. Moreover, Webb's ability to study the intergalactic medium, the diffuse gas that fills the space between galaxies, during the epoch of reionization, provides new insights into the nature of dark matter and dark energy. By mapping the distribution of this gas and its interaction with early galaxies, the telescope can help constrain models of how dark matter clumps together to form the large-scale structure of the universe. Interestingly, as of now, the James Webb Space Telescope is still in its early stages of operation. In other words, its full scientific potential is yet to be realized. Regardless, the discoveries it has already made are a testament to its transformative power. As James Webb continues to observe the early universe, it will undoubtedly provide more answers to the fundamental questions about the cosmos's origins and evolution. In the coming years, the observatory is expected to make significant contributions to our understanding of exoplanets, star formation, and galaxy evolution, in addition to its work on the early universe. Its ability to observe in the infrared will also allow it to study objects that are currently hidden from view, such as planets forming around young stars or the cores of galaxies enshrouded in dust. Moreover, Webb's discoveries will likely inspire new theories and models, prompting a deeper investigation into the nature of the universe. As we continue to explore the cosmos with James Webb, we may uncover new phenomena that challenge our current understanding, leading to a more complete and nuanced picture of the universe's history. By that time, no doubt, the question of whether it was time to overthrow the government would have been discussed countless times. After all, the Big Bang, as told, despite its success in explaining many aspects of cosmology, is not without its gaps and unresolved questions. These gaps challenge our understanding of the universe's origins and have driven ongoing research and exploration in modern cosmology. One of the most profound issues with the Big Bang theory is its treatment of the universe's initial state. The theory describes the evolution of the universe from a fraction of a second after the Big Bang onward, but it does not extend to the actual moment of creation, nor does it address the cause of the singularity itself. This leaves a gap in our understanding, a gap that science, as it currently stands, cannot fill. At the heart of the Big Bang theory lies the concept of a singularity, a point where the density of matter and energy becomes infinite, and the laws of physics as we know them break down. Singularities are deeply problematic in physics because they represent a breakdown of our understanding. In the context of the Big Bang, the singularity is a point where our current theories, namely general relativity and quantum mechanics, cease to be applicable. General relativity, which describes the force of gravity and the structure of space-time, predicts the existence of singularities under certain conditions. However, these predictions indicate that at a singularity, space-time becomes infinitely curved, and physical quantities such as density and temperature become infinitely large. In other words, the very fabric of the universe would be infinitely warped, and the physical laws that govern everything from the motion of planets to the behavior of subatomic particles would no longer hold. Quantum mechanics, which governs the behavior of particles at the smallest scales, also fails to describe what happens at a singularity. Quantum theories suggest that at extremely small scales, the fabric of space-time becomes dominated by quantum fluctuations, leading to a highly chaotic and indeterminate state. However, when combined with general relativity, these theories produce nonsensical results, such as infinite densities and curvatures. The existence of singularities in the Big Bang theory therefore suggests that our current understanding of the universe is incomplete. It implies that a more fundamental theory, possibly one that unifies general relativity and quantum mechanics, is needed to describe the true nature of the universe's beginning. In response to the limitations of the Big Bang theory, several alternative theories have been proposed to explain the origins of the universe. These theories attempt to address the question of what came before the Big Bang, or to describe a universe without a beginning at all. One such theory is the idea of a cyclic universe, where the universe undergoes infinite cycles of expansion and contraction. In this model, the Big Bang is not the beginning of the universe, but rather a transition from a previous cycle of contraction. The universe contracts into a singularity-like state, then rebounds in a new Big Bang, leading to a new cycle of expansion. This theory avoids the problem of a singularity by proposing that the universe never actually reaches infinite density, but instead undergoes a bounce at extremely high densities. Another theory is the multiverse hypothesis, which suggests that our universe is just one of an infinite number of universes that exist in a larger multiverse. According to this theory, different universes can have different physical laws and constants, and our universe may have originated from the collision or interaction of two or more universes within this multiverse. In this context, the Big Bang is simply a local event within a much larger and more complex cosmic structure. There is also the possibility that the universe had no beginning at all. Some theories propose that the universe is eternal, with no origin point. These models often involve modifications to the laws of physics to allow for a universe that has always existed in some form, without requiring a singularity or a moment of creation. For example, some versions of quantum gravity suggest that time itself may not exist in the traditional sense at the earliest moments of the universe, making the concept of a beginning meaningless. The mystery of the universe's beginning also raises profound philosophical and theological questions. If science cannot provide a complete answer to the question of the universe's origin, can these questions be addressed through other means? From a philosophical perspective, the question of the universe's beginning touches on the concept of causality, the idea that every event must have a cause. The Big Bang suggests a moment when the universe began, but what caused the Big Bang? This leads to a classic philosophical problem, the problem of the first cause. If every event must have a cause, then what caused the first cause? This line of reasoning can lead to an infinite regress, where each cause requires a preceding cause, or it can suggest the existence of a cause that itself is uncaused, an idea that some equate with the concept of God. Theological perspectives often address the question of the universe's beginning by invoking the idea of a divine creator. Many religious traditions teach that the universe was created by a deity or deities who exist outside of time and space and are not subject to the physical laws that govern our universe. This view holds that the universe had a purposeful beginning, brought into existence by an intelligent and transcendent being. However, the idea of a divine creator also raises questions. If the universe requires a cause, then what caused the creator? Some theologians argue that God is a necessary being, existing beyond the constraints of cause and effect, while others suggest that the nature of God is fundamentally mysterious and beyond human understanding. In the end, the question of the very first beginning of the universe remains one of the deepest and most enduring mysteries. While science has made tremendous strides in explaining the evolution of the universe from its earliest moments, it has yet to provide a definitive answer to what, if anything, came before the Big Bang. The singularity at the heart of the Big Bang theory points to the limits of our current understanding, suggesting that a more fundamental theory is needed to fully describe the universe's origin. At the same time, the mystery of the universe's beginning invites philosophical and theological inquiry, raising questions about the nature of causality, the existence of a first cause, and the possibility of a divine creator. These questions, like the scientific questions, remain unresolved, leaving us with the humbling realization that the origins of the universe may forever remain beyond our grasp. Another significant gap in the Big Bang theory is the horizon problem. According to the theory, regions of the universe that are separated by vast distances should not have had enough time to come into thermal equilibrium due to the finite speed of light. However, the cosmic microwave background radiation, the afterglow of the Big Bang, is remarkably uniform across the sky, with only tiny fluctuations. This uniformity suggests that distant regions of the universe must have been in causal contact with each other in the early universe, which contradicts the predictions of the standard Big Bang model. The horizon problem challenges our understanding of the early universe. It suggests that there must have been some mechanism that allowed distant regions to communicate and reach equilibrium faster than the speed of light would allow. This discrepancy led to the development of the inflationary theory, which proposes that the universe underwent a rapid exponential expansion in the first fractions of a second after the Big Bang. While inflation theory addresses the horizon problem, it is not yet fully integrated with the rest of the Big Bang framework and raises its own set of questions. Closely related to the horizon problem is the flatness problem, another gap in the Big Bang theory. Observations of the universe show that it is remarkably flat, meaning that the geometry of space is close to Euclidean. A flat universe has a delicate balance between the density of matter and energy and the rate of expansion. If the universe were slightly more or less dense, it would have quickly diverged from this flatness, leading to a very different cosmic evolution. The flatness problem is puzzling because the Big Bang theory does not inherently predict this fine-tuned balance. Without an explanation, this flatness seems coincidental, which is unsatisfying to cosmologists. The inflationary theory, again, provides a potential solution by suggesting that the rapid expansion of the early universe would have stretched its geometry, making it appear flat today. However, as with the horizon problem, inflation is an add-on to the Big Bang theory rather than a fully integrated component. One of the most profound gaps in the Big Bang theory concerns the nature of dark matter and dark energy, which together make up about 95% of the total energy density of the universe. The Big Bang theory, as it was originally formulated, accounted for the observable matter and energy in the universe, but did not predict the existence of these mysterious components. Dark matter is thought to be responsible for the gravitational effects observed in galaxies and clusters of galaxies that cannot be explained by visible matter alone. Its presence is inferred from its gravitational pull on visible matter, but it does not emit, absorb, or reflect light, making it invisible and difficult to detect directly. Despite extensive research, the exact nature of dark matter remains unknown. Dark energy, on the other hand, is even more mysterious. It is believed to be responsible for the accelerated expansion of the universe, a phenomenon that was discovered in the late 1990s. Unlike dark matter, which exerts a gravitational pull, dark energy seems to have a repulsive effect, driving galaxies apart at an increasing rate. The Big Bang theory does not explain the origin or nature of dark energy, and its discovery has led to a reevaluation of the theory. These gaps highlight the limitations of the Big Bang theory in describing the full contents of the universe. While the theory provides a framework for understanding the observable universe, it does not account for the vast majority of its energy content, leaving dark matter and dark energy as significant open questions in cosmology. Another unresolved issue in the Big Bang theory is the baryon asymmetry problem. The theory predicts that equal amounts of matter and antimatter should have been created in the early universe. However, our universe is overwhelmingly composed of matter, with very little antimatter observed. This asymmetry is puzzling because when matter and antimatter meet, they annihilate each other, producing energy. If equal amounts had been created, they should have annihilated each other completely, leaving behind a universe filled with only radiation. The existence of a matter-dominated universe suggests that some process must have created an imbalance between matter and antimatter in the early universe. Various theories have been proposed to explain this asymmetry, including mechanisms that involve slight differences in the behavior of particles and antiparticles. However, none of these theories have been confirmed, and the baryon asymmetry problem remains an open question in cosmology. The Big Bang theory provides a broad outline of how the universe evolved from a hot, dense state to its current form, but it leaves significant gaps in our understanding of how the first stars and galaxies formed. According to the theory, the early universe was a nearly uniform soup of particles, with tiny fluctuations in density. Over time, these fluctuations grew under the influence of gravity, eventually leading to the formation of the first stars and galaxies. However, the details of this process are not fully understood. For example, the exact conditions under which the first stars, known as population 3 stars, formed are still unclear. These stars are believed to have been massive, short-lived, and composed almost entirely of hydrogen and helium, as heavier elements had not yet been produced. The formation of the first galaxies, and how they evolved into the complex structures we see today, also remains an area of active research. Recent observations by the James Webb Space Telescope have begun to shed light on these early stages of cosmic evolution. James Webb's ability to observe the universe in infrared wavelengths allows it to peer back in time to see the first galaxies forming just a few 100 million years after the Big Bang. These observations are helping to fill in some of the gaps in the Big Bang theory by providing direct evidence of the early universe's structure and composition. As James Webb continues its mission, it is expected to make even more groundbreaking discoveries that will further our understanding of the early universe. Future observations will likely uncover more about the nature of population 3 stars, the formation and growth of the first galaxies, and the role of black holes in cosmic evolution. James Webb will also explore the transition from the cosmic dawn to the later stages of cosmic history, including the formation of more complex structures like galaxy clusters and the chemical enrichment of the universe. By studying the light from the earliest stars and galaxies, James Webb will help us piece together the story of how the universe evolved from a hot, dense state to the vast, complex cosmos we see today. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. Mercury should already be a dead planet. Scientists thought the humble hunk of rock that's only slightly girthier than Earth's moon would have been battered to barrenness by the sun's intense solar radiation. It's a hostile world. The day and night sides of the planet see a temperature difference of nearly 600 degrees Celsius. But Mercury has proved to be a world of contradictions, a dynamic planet that hides more surprises than scientists initially gave it credit for. A thin atmosphere, a magnetic field, and a stash of volatile compounds still persist on Mercury, features that scientists usually associate with planets that are larger and farther away from the Sun. While new observations from the last few decades have given scientists good cause to revise their opinion of Mercury.
Mercury is basically a big ball of metal surrounded like a tiny bit of rock. And the major question is, why? Why is it like this when the rest of the planets aren't?
Its secrets remain. But now, by using powerful telescopes, scientists have stumbled upon these secrets. But what they found is so weird. There is something moving that they never saw anywhere else. Such a stunning revelation could even lead to crucial missions to reveal a terrifying truth about our universe. Join us as we shed light on the dark shadow that Mercury has kept under wraps. Named for the fleet-footed Roman messenger god, Mercury is the closest planet to the Sun, zipping around our parent star at an average of 36 million miles away. However, Mercury's orbit is not a perfect circle. The planet can pass as close as 29 million miles and as far away as 43 million miles. Living up to its name, Mercury is the fastest planet in the solar system, speeding along at about 29 miles per second and completing each orbit around the Sun in just 88 Earth days. Mercury is also the smallest planet in the solar system, measuring just 3,032 miles wide at its equator. That makes it only slightly larger than Earth's moon. Because Mercury is so small and so close to the Sun, it is the most elusive of the 5 planets that are visible to the naked eye. You can only catch Mercury at dawn and dusk, and it usually does not rise far above the horizon. But that's not the only time the tiny planet makes an appearance. Because of its position in the solar system, Mercury passes between Earth and the Sun 13 times each century in an event known as a transit. During a transit of Mercury, observers on Earth can see the planet in silhouette as it seems to sweep across the Sun's disk. Since ancient times, people observing the heavens have noticed that the naked eye planets sometimes appear to move backward, briefly shifting from their usual eastward motion to a westward path across the sky. This retrograde motion is an illusion created when one planet moves faster in its orbit than another, so that it catches up to and passes the slower world. For observers on Earth, Mercury is in retrograde about 3 to 4 times a year. If you could watch the skies from the surface of Mercury, you would sometimes catch the rare sight of the Sun in retrograde. As Mercury makes its closest approach to our smoldering star, its orbital speed exceeds its rate of rotation on its axis. That means someone standing on Mercury would see the Sun start to rise, then briefly set, then rise again, all within the same day. Like the other planets in the solar system, Mercury was born about 4.5 billion years ago, condensing from the swirling ring of dust and gas left over from the Sun's formation. The small planet cooled very quickly, contracting enough within the first billion or so years to prevent magma from escaping through the outer crust and ending geologic activity such as volcanism on the surface. And while Mercury may be small, it's hefty. Although its diameter is barely larger than the Moon's, Mercury is over 4 times as massive as Earth's natural satellite. In fact, Mercury is the second densest planet in our solar system, after Earth. The planet's extreme density comes from the fact that it has a large iron core that makes up about 60% of the planet's volume. In contrast, Earth's core by volume is only about 15%. The abnormal internal structure has spawned several theories on Mercury's birth. Scientists think that perhaps early Mercury's outer layer was boiled away by the Sun or scattered by solar winds. Or perhaps the young planet could have been struck by a large impactor that stripped away most of the softer outer layer, leaving behind its sturdier heart. Since part of the mantle and crust are still present today, this suggests that the collision may not have been a head-on smack, but a glancing brush that preserved some of Mercury's original layers. The first mission to Mercury, Mariner 10, was launched in 1973 and found that Mercury still sustains a magnetic field. The discovery came as a shock to the scientific community, who had assumed that such a small planet would have rapidly cooled, and its insides would have congealed, thereby losing any means of magnetism at the global scale. The presence of a magnetosphere implies that part of Mercury's core is still churning. Mercury's magnetic field is about 100 times weaker than Earth's on their respective planetary surfaces. The sluggish dynamo means that the planet is at the tail end of its developmental stage, on its way to becoming a dead planet like Mars. In the 2010s, the second Mercury mission, Messenger, documented that the planet's magnetic field is off-kilter. The magnetic South Pole doesn't sit on the geographic South Pole. Instead, it is buried almost at the center of the planet. The magnetic field offers a glimpse of the planet's interior and a snapshot of its history, hinting at how far the whirling insides have decelerated over billions of years. Due to its proximity to our star, Mercury is hot. If we're being quantitative, it's actually extremely hot. As the closest planet to the Sun, it completes an orbit in just 88 Earth days, achieving a maximum temperature during the day of a whopping 427 °C at its hottest equatorial locations. Mercury rotates very slowly, so its night side spends a consecutively long time in the dark, shielded from the Sun. During those times, it gets down to just minus 173 degrees. That low temperature is incredibly cold, and far colder than any known naturally occurring temperatures here on Earth. But despite being the closest planet to the Sun, Mercury is not the hottest planet in the solar system. Venus is about twice as far from the Sun on average as Mercury is, taking about 225 Earth days to orbit the Sun. It also rotates even slower than Mercury, spending more than 100 consecutive Earth days at a time bathed in sunlight, and then an equal amount of time in darkness. And yet, when you measure the temperature of Venus, there's a surprise. Venus is the same temperature at all times, day or night, at an average of 462 °C, making it even hotter than Mercury. This strange occurrence did more than just puzzle astronomers when they first discovered it. It mortified them. Venus wasn't large enough to generate its own heat, and yet it was hotter at Venusian midnight than at Mercurian high noon. Why is that? Well, that is because of the main difference between the two worlds. Venus has a very substantial one that's some 190 times as thick as Earth's is, but Mercury, instead of a substantial atmosphere, has such a thin atmosphere that it doesn't really qualify as an atmosphere. Instead, scientists call this wispy layer of gas an exosphere, where the gas is so rarefied that it hardly registers a pressure reading. Mercury takes a constant beating from the Sun, so its exosphere has to regenerate itself from the surface. Since the 1980s, astronomers have detected in Mercury's exosphere atomic sodium, potassium, and calcium, metals with strong emission signals that can be observed all the way from Earth with telescopes. These metallic elements are not usually thought of as gases, but they find their way into Mercury's skies by dint of solar particles and meteorites striking the planet's surface. Solar winds gouge the resulting exosphere, and the interactions between the gases and sun-flung particles fashion a 15 million mile-long glowing tail behind Mercury. This tail lengthens and shrinks seasonally, depending on Mercury's proximity to the Sun. If you were standing on Mercury and looking up at the right time of the year, Mercury's long tail would appear in the sky as a faint orange glow, as if the heavens were illuminated by sodium streetlights. A planet perched right at the sun's maw shouldn't harbor any water, let alone ice, or so researchers thought. But in the 1990s, scientists at Goldstone in California and the Arecibo radio telescope in Puerto Rico directed a stream of radar signals toward Mercury. The teams were astonished to observe two brightly reflective spots at the poles, likely icy deposits. In 2012, MESSENGER confirmed that the ice at Mercury's North Pole was frozen water. Laser measurements on board identified carbon-rich material on the surface that insulates an ice pack underneath. Mercury has managed to cling on to its water because it has pockets in permanent shadow. Relative to its orbit around the Sun, the planet spins perfectly upright, like a soldier at attention facing a commanding officer. That means the impact craters near the poles have insides that never see any daylight. Temperatures within these divots dip below minus 173 degrees Celsius, close to the temperature where nitrogen gas liquefies. It's cold enough that ice can be stable over geological timeframes. And as on most other rocky planets, the water on Mercury probably came from asteroids that crash-landed onto the surface. This water hides in Mercury's craters, untampered with since primordial times. On other terrestrial planets in the solar system, geological processes such as weather cycling have scattered the externally delivered water all around the globe. If scientists want to sample ancient ice in its pristine form in the solar system, the best source is probably Mercury's poles. Mercury defied expectations again when MESSENGER detected volatiles on the sun-scorched world. Volatiles are chemicals that can jump between solid and gas phases in a short temperature change. Mercury already proved it sheltered water, a volatile, but MESSENGER found others such as sulfur, potassium, and chlorine that easily vaporize at moderately high temperatures. These volatiles are distributed all across the surface of the planet. For its size, Mercury contains as much volatile content as other terrestrial planets in the solar system that are farther from the Sun and hence much colder. Where the volatiles come from and how Mercury has retained them are still matters of scientific debate. Some researchers think that the volatiles came from underground relatively recently, while others think the chemicals have persisted on the surface since an embryonic Mercury condensed from its protoplanetary disk. The volatiles on Mercury raise questions. For example, if planets that edge up against their stars have volatiles, especially water, could these locales also be habitable? Well, it's possible that Mercury once held the ingredients for life. Indeed, Mercury has irregular depressions in the ground called hollows. Mariner 10 first glimpsed them in 1975. Then, MESSENGER photographed these shallow tracts at fine resolution. The depressions span from a few dozen feet to over a mile across, and they may be as deep as 120 feet. They look like the soft, airy insides of a sourdough loaf cut open. The hollows may be the doing of volatiles, scientists theorize. Since the atmosphereless Mercury has no rain or wind to carve the land, surface features like hollows can only be formed from other processes, such as the ground leaking volatiles into space. Hollows are relatively young formations, about 100,000 years old on average, compared with some 4 billion-year-old impact craters on Mercury. Scientists think hollows are still forming today, and hollows are unique to Mercury. No other celestial body in the solar system seems to present similar pockmarks. In recent years, scientists have identified other structural formations on Mercury, chaotic terrains, jumbled ridges that look like a failed game of Jenga, cut up vast swaths of the land. Some researchers think the chaotic terrains are the result of the ground wafting volatiles until it loses structural integrity and collapses. Other scientists think that chaotic terrains form after ripples from an asteroid impact encircle the planet and meet on the opposite side of the globe. In addition, Mercury's topography also provides clues that volcanoes once spewed lava on the planet. Mariner 10. First glimpsed and then Messenger later confirmed that glossy plains spread across Mercury's surface. Each plain suggests pooled lava smoothed over older craters and ridges. Researchers think that magmatic volcanism halted on Mercury anywhere between 1 billion to 3.5 billion years ago, due to planetary cooling and contraction that plugged up the magma's escape routes. Mercury has also shown signs of another kind of volcanism, explosions. If streaming lava is like a runny nose, then explosions are the volcanic equivalent of a sneeze. Irregular pits several miles across and more than 2 miles deep hint at ancient pyroclastic volcanoes that self-destructed. Scattered around these pits are deposits that researchers think are ejecta from the explosion. These types of volcanic bursts are probably caused by volatiles underground. When these buried chemicals rise to the surface, they expand in volume. Eventually, the pressure buildup of gases causes the volcano to pop, like an overfilled balloon. But volatiles, a chemical category that includes water, are essential for sparking and supporting life as we know it here on Earth. So, their potential presence on Mercury is an intriguing development. Astronomers now speculate that beneath the scorching surface of Mercury, the closest dwarf planet to the Sun, there could be signs of life. But how could volatiles, which are essential to life here on Earth, survive on a planet whose daytime temperatures soar to 430 degrees Celsius and drop to minus 180 degrees Celsius at night? Alexis P. Rodriguez, a researcher at the Planetary Science Institute in Arizona, explained that while the planet's surface swings wildly between temperature extremes, just below the surface, temperatures are milder. In the words of Rodriguez, it's likely that there was some sort of water that formed in part of Mercury's crust. But the team cannot yet tell exactly what volatiles were present when the planet's surface broke apart. While the mystery remains, a completely unexpected discovery made by NASA's Messenger spacecraft revealed that a 10-mile-thick diamond mantle may lie beneath the crust of Mercury. While instance of such valuable encrustation might sound tantalizing, turning these precious stones into fashionable jewelry remains an impossibility due to their inaccessible location deep within the planet. However, these gems could hold the key to unraveling some of the big unanswered questions circling around Mercury composition and its rather curious magnetic field. These diamonds may facilitate heat transfer between the core and mantle, thereby creating temperature differences and causing liquid iron to circulate, a process that would kickstart the creation of a magnetic field. The discovery of a potential diamond layer within Mercury opens new avenues for planetary research and composition studies, not only of Mercury, but also of other celestial bodies. Understanding the unique geological characteristics of Mercury could provide deeper insight into the formation and evolution of the solar system. The new discovery also prompts a reconsideration of the processes involved in planetary formation. Diamonds are typically associated with high-pressure environments, suggesting that similar conditions may exist in other distant rocky exoplanets and moons within our solar system. Studying extreme planetary conditions can reveal not only the composition of these bodies, but also the historical processes that formed them, leading to a more comprehensive understanding of geology across the cosmos. The potential discovery casts a new light on the evolution of carbon-rich exoplanets. The process that led to the formation of a diamond layer on Mercury could also be at play on other planets, possibly leaving similar traces. The arrival of the Bepi-Colombo spacecraft, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency, in 2025 will provide better opportunities to delve deeper into this intriguing discovery. Bepi-Colombo was launched in 2018 on a complex trajectory to the solar system's innermost planet. The ESA reports that the spacecraft's thrusters have lost some power. Bepi-Colombo's mission is to complete a comprehensive investigation of Mercury's magnetosphere, magnetic field, and internal and external structure. But traveling around in the inner solar system is complicated, and the Bepi-Colombo spacecraft will use more energy getting to Mercury than it takes to get to Pluto. The spacecraft will perform 9 planetary flybys before reaching its destination at the end of 2025. Bepi-Colombo has already performed 1 gravity assist at Earth, 2 at Venus, and 5 at Mercury. It'll perform 1 more at Mercury in January 2025. The Mercury Transfer Module, or MTM, is the part of the spacecraft that delivers a pair of orbiters to Mercury. On April 26th, as the spacecraft was about to execute its next maneuver, the MTM didn't deliver enough electrical power to its thrusters. A team working on it restored the thrust back to 90% on May 7th. But the MTM still isn't delivering enough electricity to get back to 100% thrust. Despite the power problems, the spacecraft is on track to complete its final Mercury flyby. A team is working to maintain the current power level and to understand how the diminished thrust will affect future maneuvers. They're also working on restoring full power to the thrusters. To facilitate this, the mission's flight control team at the European Space Operations Center in Darmstadt, Germany, has arranged additional ground station passes. Bepi-Colombo employs a solar electric propulsion system. 2 15-meter-long solar cells gather energy and deliver it to 4 ion thrusters that use xenon propellant. The thrusters are mounted on gimbals, making them aimable. Bepi-Colombo consists of 3 separate spacecraft. The Mercury Transfer Module is kind of like a tugboat, delivering 2 separate orbiters to Mercury. One of the orbiters is the Mercury Planetary Orbiter, and it carries 11 scientific instruments, including cameras, several spectrometers, a magnetometer, and others. The other one is the Mercury Magnetospheric Orbiter, largely built by JAXA. It carries 5 groups of instruments, including 1 group that will study the plasma and neutral particles from the planet, its magnetosphere, and the solar wind. While waiting for the first data obtained by Bepi-Colombo, scientists also put their hope in another tool, the James Webb Space Telescope. The Supreme Space Telescope comes with significant advantages over any previous mission. First and foremost is its size. James Webb features a 21.7-foot mirror composed of 18 gold-plated hexagonal segments. This colossus gathers more than 6 times as much light as the Hubble Space Telescope's 7.8-foot mirror, so it can record light from objects 6 times faster than its predecessor. But Webb's sensitivity to infrared light is the real game-changer. The Space Telescope can view wavelengths from the red end of the visible spectrum to the mid-infrared. Hubble's optics are optimized to record radiation from the ultraviolet to the near-infrared, with the majority of its sensitivity centered on visible light. Perhaps surprisingly, in its intended infrared domain, James Webb generally won't resolve finer details than Hubble achieves in optical light. Although resolution increases with mirror size, it also diminishes with wavelength. Observing in the infrared allows astronomers to see galaxies that existed less than 1 billion years after the Big Bang. These distant objects emit ultraviolet and visible light, but the expansion of the universe shifts this radiation to longer infrared wavelengths. Peering into the infrared is the only way to observe these young galaxies from Earth's vicinity. The same holds true for newly forming stars. The dust that envelops infant suns scatters visible light, hiding what lies within from our eyes, but it lets infrared radiation largely pass through. Despite its focus on distant galaxies and star formation, James Webb is an all-purpose observatory. Its powerful infrared eye sees details in solar system objects beyond the reach of conventional telescopes. Early observations include studying cloud belts on the gas and ice giant planets, tracking cloud formations on Saturn's largest moon, Titan, exploring Pluto's climate, and probing many of the smaller asteroids and trans-Neptunian objects that populate the outer solar system. The telescope even observed the asteroid moonlet Dimorphos in September, when NASA's double asteroid redirection test slammed into it. The impact slightly changed the object's orbit around its parent body, Didymos, helping the space agency assess its ability to alter the course of potentially hazardous asteroids that could cross Earth's path. Thus, it's not far-fetched to think of the Space Observatory can take a closer look at Mercury, unlocking the subterranean secrets of the closest planet to the Sun. In the latest observation, using James Webb, astronomers discovered that Ariel, a moon of Uranus, could be hiding in a buried liquid water ocean. The discovery could supply an answer to a mystery surrounding this Uranian moon that has perplexed scientists. The fact Ariel's surface is covered with a significant amount of carbon dioxide ice. This is puzzling because at the distance, Uranus and its moons exist from the Sun. 20 times further out from the Sun than Earth, carbon dioxide turns to gas and is lost to space. This means some process must refresh the carbon dioxide at the surface of Ariel. Previous theories have suggested this happens as a result of interactions between Ariel's surface and charged particles trapped in Uranus's magnetosphere that provide ionizing radiation, breaking down molecules and leaving carbon dioxide, a process called radiolysis. However, new evidence from the Webb telescope suggests the source of this carbon dioxide could come not from outside Ariel, but from its interior, possibly from a buried subsurface ocean. Because chemical elements and molecules absorb and emit light at characteristic wavelengths, they leave individual fingerprints on spectra. The team behind this discovery used James Webb to gather spectra of light from Ariel, which helped them paint a picture of the chemical makeup of the Uranian moon. Comparing this to simulated spectra from a chemical mix in the lab here on Earth revealed to the team that Ariel has some of the most carbon dioxide-rich deposits in the solar system. Not only did this add an extra 0.4 inches of thickness to the ice on the side of the tidally locked Ariel that permanently faces away from Uranus, but it also revealed clear deposits of carbon monoxide for the first time. As team leader Richard Cartwright from the Johns Hopkins Applied Physics Laboratory, or APL, said in a statement, "It just shouldn't be there. You've got to get down to 30 kelvins, minus 405 degrees Fahrenheit, before carbon monoxide's stable. The carbon monoxide would have to be actively replenished, no question. That's because Ariel's surface temperature is, on average, around 18 degrees Celsius warmer than this key temperature." Cartwright acknowledges that radiolysis could account for some of this replenishment. However, observations from Voyager 2's 1986 flyby of Uranus and its moons and other recent findings have suggested that the interactions behind radiolysis could be limited because Uranus's magnetic field axis and the orbital plane of its moons are offset from each other by about 58 degrees. That means that the majority of the carbon-oxygen compounds seen on Ariel's surface could be created by chemical processes in a liquid water ocean trapped under ice on Ariel. Once created in the seep water ocean of Ariel, these carbon oxides could then escape through cracks in the icy shell of the Uranian moon, or could even be explosively ejected by powerful eruptive plumes. Scientists have suspected for some time that the cracked and scarred surface of Ariel may indicate the presence of active cryovolcanoes, volcanoes that erupt plumes of icy slush rather than lava. These plumes could be so powerful that they launch material into Uranus's magnetic field. The majority of the cracks and grooves seen on the surface of Ariel are located on the side of the moon that faces away from Uranus. If carbon dioxide and carbon monoxide are leaking from these features to the surface of the Uranian moon, this could explain why these compounds are found in greater abundance on this trailing side of the icy body. In addition, James Webb also picked up more chemical evidence of a subsurface liquid water ocean. Spectral analysis hinted at the presence of carbonate minerals, salts created when rock meets and interacts with liquid water. As Cartwright explained, if our interpretation of that carbonate feature is correct, then that is a pretty big result because it means it had to form in the interior. That's something we absolutely need to confirm, either through future observations, modeling, or some combination of techniques. Uranus and its moons haven't been visited by a spacecraft since Voyager 2 almost 4 decades ago, and this wasn't even the spacecraft's primary mission. In 2023, the Planetary Science and Astrobiology Decadal Survey emphasized the need to prioritize a dedicated mission to the Uranian system. Cartwright believes such a mission would present an opportunity to collect valuable information about Uranus and Neptune, the solar system's other ice giant. Such a mission could also deliver vital data about the other potentially ocean-bearing moons of these systems. This information could then be applied to extrasolar planets or exoplanets beyond the solar system. As team member and NASA Applied Physics Laboratory scientist Ian Cohen said, all these new insights underscore how compelling the Uranian system is, whether it's to unlock the keys to how the solar system formed, better understand the planet's complex magnetosphere, or determine whether these moons are potential ocean worlds. Many of us in the planetary science community are really looking forward to a future mission to explore Uranus. In another remarkable study made by James Webb, astronomers have investigated a new super-Jupiter planet that is one of the coldest worlds ever seen outside the solar system. The exoplanet is located in the triple star system Epsilon Indi, which sits around 12 light-years away. The planet is designated Eps Ind Ab and has a mass around 6 times that of Jupiter. It orbits its red dwarf parent star at a distance similar to that between Neptune and the Sun. This gives the world a surface temperature of around 0 degrees Celsius and means one orbit of the planet takes around 200 Earth years. The Webb telescope was able to image the exoplanet using the sensitive infrared capabilities of the mid-infrared instrument. The investigation of Eps Ind Ab could help astronomers better understand the evolution of gas giant planets and their systems. This is the first time that the powerful space telescope has been able to image an exoplanet that wasn't previously imaged from the ground. Eps Ind Ab is also the coldest exoplanet James Webb has been able to study thus far. That's why scientists were excited when we realized we had imaged this new planet. To their surprise, the bright spot that appeared in our MIRI images did not match the position we were expecting for the planet. They added that previous studies had correctly identified a planet in this system, but had underestimated the super-Jupiter gas giant's mass and orbital separation. The team was able to correct this with the help of James Webb. The crew determined the planet has a highly elliptical, or flattened, orbit that, at its closest, brings it to a distance about 20 times the distance between Earth and the Sun. At the furthest point in its orbit, Eps Ind Ab is 50 times further away from its parent star than the average distance between Earth and the Sun. The world's parent star, a red dwarf named Eps Ind A, has 2 stellar companions. Both are brown dwarfs, or failed stars, named as such because they're objects that form like stars but can't gather enough mass to trigger nuclear fusion processes in their core that define what a main sequence star is. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. In the vast expanse of our solar system, the quest for extraterrestrial life has led scientists to some of the most unexpected and distant corners. One such destination, rich with the potential for harboring life, is Saturn's icy moon, Enceladus. And in a stunning revelation, researchers have just unveiled astonishing evidence suggesting this small, bright moon, only about 500 kilometers in diameter, has become one of the most promising candidates for finding life beyond Earth. But what exactly have the experts found on the icy moon? Is humanity standing on the cusp of a new era where the search for extraterrestrial life could be dramatically altered forever? All this and more will be discussed in today's episode. Enceladus was first discovered by the German-born British astronomer William Herschel in 1789. However, it remained largely unremarkable for nearly 2 centuries, overshadowed by its larger siblings in the Saturnian system, like Titan. It wasn't until the late 20th century, with the arrival of advanced spacecraft like Voyager and later Cassini, that Enceladus began to reveal its secrets. The Voyager missions of the early 1980s provided the first close-up images of Enceladus, showing a bright, icy surface with a striking lack of craters. This suggested that the moon was geologically active, resurfacing itself and erasing the evidence of past impacts. However, it was the Cassini-Huygens mission, launched in 1997 and arriving at Saturn in 2004, that truly revolutionized our understanding of Enceladus. Cassini's exploration of Enceladus began in earnest in 2005, when the spacecraft made its first close flyby of the moon. What it found stunned the scientific community. Cassini has been making discovery after discovery that has catapulted Enceladus to one of the top places to look for life beyond Earth. In particular, we learned Enceladus has a liquid water ocean beneath its icy surface, heated by gravitational tidal forcing, the kind of forcing that produces ocean tides on Earth. This environment is tantalizingly similar to the hydrothermal vents thought by some to be the place where life may have originated on Earth. Such vents certainly host life on Earth today. Most life on Earth ultimately relies on photosynthesis, generating energy from sunlight. Meanwhile, the ultimate energy source for any life on Enceladus would be the gravity of Saturn producing tides far stronger than the moon produces on Earth, allowing a liquid water ocean despite the very cold 200°C ice crust surface. The Enceladus plumes have been called a gimme for efforts to sample the oceans of alien worlds. One wouldn't need to land to collect a sample, nor to then launch to return it for analysis. An obvious approach to sampling an ice volcano is to simply fly through it. However, this is difficult because the speed at which a space probe would encounter the plume would likely kill most organics. Instead, the easiest approach is to examine the accumulation of ejected material from Enceladus in Saturn's A ring, which is what the team did in this latest study. Using this approach, researchers have previously discovered complex organic molecules coming from Enceladus. These findings confirmed that the watery environment on Enceladus supports complex chemistry involving nitrogen and oxygen. However, until now, we didn't know about the availability of phosphorus on Enceladus. Phosphorus is a vital ingredient because it is needed for the phosphate groups, phosphorus plus oxygen, that link the long chains of nucleic acids, such as DNA and RNA, that store genetic information. It also allows cells to store energy by means of molecules, such as adenoside triphosphate, ATP for short. Of course, we don't know for sure that life inside Enceladus, if it exists, is obliged to use nucleic acids or ATP. However, because the presence of phosphorus is essential for life as we know it, it makes Enceladus a more likely prospect now that we are certain that there is enough phosphorus available there. And as expected, the intriguing new findings estimate that concentrations of phosphorus on Enceladus are at least 500 times higher than the highest known concentrations in Earth's oceans. The discovery shows that the icy moon, already one of the hottest candidates in the search for alien life, now satisfies the strictest requirement of habitability. The team found Enceladus's phosphorus by avoiding the cluttered data collected during the Cassini's frantically quick zooms through the plumes. Instead, they scoured sparser data accumulated in a more leisurely fashion by Cassini's cosmic dust analyzer during 15 periods between 2004 and 2008, while Cassini was traveling within one of Saturn's rings, the E-ring. Enceladus travels along this hoop as it orbits. The E-ring hoop is more than 2,000 kilometers thick. About 30% of the ice particles emitted in Enceladus's plumes end up there, as demonstrated by a recent image from the James Webb Space Telescope, which is the only proof we have that the plumes were still active 5 years after the end of the Cassini mission. Sorting through analyses of nearly 1,000 ice particles, which are believed to represent frozen spray from Enceladus, the researchers found 9 of them that contained phosphates. This may sound like a slim haul, but it is enough to demonstrate that Enceladus has more than enough dissolved phosphorus in its ocean to permit the functioning of life there. Indeed, follow-up laboratory experiments suggest that the concentration of dissolved phosphorus in Enceladus's ocean water may even be hundreds of times greater than in Earth's oceans. The discovery has implications beyond Enceladus's corner in the solar system. Phosphorus is quite rare in natural waters, as it readily reacts with positively charged atoms like calcium to form calcium phosphate, which locks up the phosphorus and thus makes it unusable for life forms. But Enceladus is able to host such high amounts of dissolved phosphorus because it has what scientists call a soda ocean. Soda oceans, or soda lakes, are rich in carbonates, minerals that contain carbon dioxide and form easily in water. Carbonates bond with other elements, like calcium, leaving phosphorus available for potential life to use. This process can be witnessed on Earth, too. California's Mono Lake, Nevada's 2 soda lakes, and the Borax Lake in Oregon are just a few examples of soda lakes where rich ecosystems are able to survive. Elsewhere in the world, Africa, Asia, and Europe are known to harbor similar soda lakes. In the solar system, celestial objects which host oceans beyond the frost line, the arbitrary point in the system between the asteroid belt and Jupiter's orbit, beyond which carbon and ice begin to condense into solid ices, would inevitably have a soda ocean. After all, with many of the essential components necessary for the emergence of life, as we know it, have thus been discovered on Enceladus, this puts it at or near the top of lists of places to search for life beyond Earth in our solar system. Nevertheless, this discovery is only the start of the story. For phosphate to form bonds with carbon, this type of bond is found in the backbone of DNA. We need specialized chemistry that's very dependent on the environment. We'll need further study of the chemistry in and under the crust of Enceladus. Fascinatingly, several mission concepts have been proposed to further investigate the potential for life on Enceladus. These include flyby missions that would sample the plumes in greater detail, as well as more ambitious proposals for landers or even probes that could penetrate the ice shell and explore the ocean directly. One of the most promising mission concepts is the Enceladus Orbilander, which would combine an orbiter and a lander in a single spacecraft. The orbiter would study the moon from above, mapping its surface, analyzing the composition of the plumes, and searching for signs of habitability. The lander, meanwhile, would touch down on the surface, possibly near one of the active geysers, and conduct detailed studies of the ice and any material that may have been deposited by the plumes. Another concept is the Enceladus Life Finder, also known as ELF, a proposed mission that would fly through the plumes and use advanced instruments to search for biosignatures, indicators of life, such as specific patterns of organic molecules or isotopic ratios that are unlikely to be produced by non-living processes. While these missions remain in the proposal stage, the interest in Enceladus is high, and it is likely that future missions will be launched to further explore this intriguing moon. The search for life on Enceladus is not just about finding organisms in a distant ocean, it's about answering fundamental questions about the nature of life in the universe. If life can exist on Enceladus, it would suggest that life is not a rare phenomenon, but rather a common outcome of the right environmental conditions. That simply would have profound implications for our understanding of the universe and our place within it. For centuries, humanity has wondered whether we are alone in the cosmos. The detection of even the most primitive life forms on another world would suggest that life is not unique to Earth, but rather a natural consequence of the right combination of ingredients and conditions. Such a discovery would also have significant implications for the field of astrobiology, the study of life in the universe. It would provide a second example of life, allowing scientists to compare and contrast it with life on Earth. This, in turn, could lead to a better understanding of the fundamental principles that govern the emergence and evolution of life. Moreover, finding life on Enceladus would raise new questions about the distribution of life in the solar system and beyond. If life can exist on a small, icy moon with a subsurface ocean, it might also be present on other icy bodies, such as Europa, another moon of Jupiter, or even on distant exoplanets with similar conditions. The discovery would fuel the search for life in other parts of the solar system and potentially beyond. While the potential for life on Enceladus is exciting, there are significant challenges to overcome. One of the primary challenges is ensuring that future missions to Enceladus do not inadvertently contaminate the moon with Earth life. This is crucial because it could compromise the search for indigenous life forms and make it difficult to distinguish between Earth-born organisms and potential Enceladan life. Additionally, the harsh conditions on Enceladus, extreme cold, high radiation levels, and the difficulty of accessing the subsurface ocean pose technical challenges for exploration. Developing the technology to safely and effectively explore Enceladus, whether by sampling the plumes or drilling through the ice, will require significant advancements in engineering and planetary protection. Despite these challenges, the scientific community remains optimistic about the prospects of exploring Enceladus further. The discoveries made by the Cassini mission have opened a new chapter in the search for life in the solar system, and Enceladus stands out as one of the most promising locations for finding answers to some of the most questions in science. On the other hand, note that the deeper we look into space, the more places we come across that maybe, just maybe, could host life. From our neighboring planets to distant galaxies sending out weird signals, the list of spots in space worth checking out just continues to grow. And here are the best places to search for life in our vast universe. 1. Mars, the red planet. Mars has captivated human imagination for centuries as a potential abode of life. The discovery of dried-up riverbeds, polar ice caps, and minerals that form in liquid water strongly suggest that Mars once had a more temperate climate and liquid water on its surface, key ingredients for life as we know it. Although the surface of Mars today is harsh and inhospitable, with extreme cold, radiation, and a thin atmosphere, the possibility of life cannot be ruled out. NASA's Perseverance rover, currently exploring the Jezero crater, is on a mission to search for signs of ancient microbial life. The crater was once home to a lake, making it an ideal location to find preserved biosignatures. Perseverance is equipped with sophisticated instruments designed to analyze soil and rock samples for organic molecules, the building blocks of life. If life ever existed on Mars, evidence might still be trapped in its subsurface, shielded from the harsh surface conditions. 2. Europa, Jupiter's icy moon. Europa, one of Jupiter's largest moons, is a prime candidate in the search for extraterrestrial life. Beneath its thick ice crust lies a subsurface ocean, which could contain twice as much water as all of Earth's oceans combined. This vast ocean, kept warm by tidal forces from Jupiter's gravity, might be an ideal environment for life. The icy shell of Europa is constantly being resurfaced, which suggests that the ocean beneath could be interacting with the surface, possibly bringing nutrients and energy sources from the moon's interior. The upcoming Europa Clipper mission, set to launch in the 2030s, will conduct detailed reconnaissance of Europa's ice shell and subsurface ocean. It will look for conditions suitable for life and attempt to identify any potential biosignatures. 3. Titan, Saturn's largest moon. Titan, the largest of Saturn's moons, presents a unique environment in the search for life. Unlike any other body in our solar system, Titan has lakes and rivers of liquid methane and ethane on its surface, and a thick atmosphere rich in organic compounds. While its surface temperature is far too cold for liquid water, the possibility of life, perhaps life forms that use methane instead of water as a solvent, cannot be dismissed. Titan's subsurface ocean of water mixed with ammonia adds another layer of intrigue. The Huygens probe, which landed on Titan in 2005, revealed a landscape shaped by both erosion and deposition, similar to Earth's. The upcoming Dragonfly mission, planned for the mid-2030s, will explore Titan's surface and atmosphere in detail. This rotorcraft lander will investigate the prebiotic chemistry of Titan and assess its potential habitability. 4. Venus, Earth's twin with a twist. Venus, often referred to as Earth's twin due to its similar size and proximity to the Sun, presents a paradox. While its surface is a hellish environment with temperatures hot enough to melt lead and a crushing atmosphere, the upper layers of its thick clouds offer a potential haven for life. In 2020, the detection of phosphine gas in Venus's clouds, an unexpected and controversial finding, sparked renewed interest in the planet as a candidate for hosting life. Phosphine on Earth is produced by microbial life in oxygen-free environments. If this gas is indeed present in Venus's atmosphere, it raises questions about its origin, as known non-biological processes should not produce it in the observed quantities. While the surface of Venus is extremely inhospitable, the cloud tops, where temperatures and pressures are more Earth-like, could potentially harbor microbial life. Future missions to Venus, such as the Veritas and Da Vinci Plus missions, aim to further investigate its atmosphere and surface. 5. Exoplanets in the habitable zone. Beyond our solar system, thousands of exoplanets have been discovered, with many located in the so-called habitable zone, the region around a star where conditions might be right for liquid water to exist. These exoplanets represent the most tantalizing targets in the search for life, as some could be Earth-like in size and composition. One of the most studied exoplanets is Proxima Centauri b, located just 4.34 light-years away in the habitable zone of the star Proxima Centauri. Another promising candidate is TRAPPIST-1e, one of 7 Earth-sized planets orbiting the ultra-cool dwarf star TRAPPIST-1. These planets are of particular interest because they are close enough for us to study their atmospheres in detail using the James Webb Space Telescope. Launched in December 2021, James Webb has already begun providing detailed observations of exoplanet atmospheres, searching for signs of water vapor, methane, and other potential biosignatures. The discovery of these elements could hint at the presence of life, or at least the potential for habitability. While the search for microbial life focuses on natural biosignatures, another avenue of exploration is the search for technosignatures, evidence of advanced civilizations. This includes detecting radio signals, laser emissions, or even the dimming of a star caused by massive structures like Dyson spheres. For those who don't know, the idea behind a Dyson sphere is to collect as much energy from a star as possible. On Earth, the total amount of energy we receive from the Sun, a value known as the total solar irradiance, is 1,361 watts per square meter, as measured by NASA's Solar Radiation and Climate Experiment. But that is just a tiny proportion of the Sun's total energy output, radiated in all directions, which is 380 billion quadrillion watts every second. Because Earth is so small by comparison, we receive only a tiny proportion of this energy. However, Suppose that an enterprising technological civilization wanted to make use of all their star's energy that would otherwise move off into space at the speed of light. If they had sufficiently advanced technology, they might build themselves a Dyson sphere, a spherical swarm of solar energy collectors that would fully encapsulate their star and collect all of its energy. Scientists who study the search for extraterrestrial intelligence, also known as SETI, categorize a civilization with a Dyson sphere as a Kardashev Type 2 on the Kardashev scale, meaning it's capable of utilizing all the energy from a star in the region of 1026 watts per second. This value varies from star to star, as some stars are more or less luminous than the Sun. A Type 1 civilization utilizes all of the energy available to a single planet: fossil fuels, renewable energy sources, and nuclear power, which is calculated to be about 1016 watts per second. And a Type 3 civilization utilizes all the power in an entire galaxy by building Dyson spheres around every star and taking energy from the central supermassive black hole, and attains 1036 watts per second. If you're wondering where we rate on that scale, we're currently a Kardashev Type 0.7449 civilization. We don't even make full use of all the energy available to us on Earth. The Breakthrough Listen project is one of the most ambitious efforts in this domain, using the world's largest radio telescopes to scan the skies for artificial signals. Although no definitive signals have been found so far, the search continues, expanding to new targets and frequencies. The discovery of technosignatures would not only confirm the existence of intelligent life, but also offer profound implications for our understanding of the universe. As our understanding of the cosmos grows, so too do the methods and technologies we employ to search for life. Future missions and projects are poised to expand our reach, both within our solar system and beyond. For example, the Europa Clipper and Dragonfly missions will provide unprecedented data on the habitability of icy moons. Moreover, the development of next-generation telescopes, such as the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT, will allow us to study exoplanets in even greater detail, potentially identifying more candidates for life. These instruments will be capable of analyzing the atmospheres of exoplanets with incredible precision, looking for chemical imbalances that might indicate biological processes. The search for life beyond Earth is a journey that spans the vastness of space and the depths of time. From the ancient riverbeds of Mars to the icy oceans of Europa and Enceladus, and the distant exoplanets bathed in the light of alien suns, each location offers a unique glimpse into the potential for life elsewhere in the universe. As our technology advances and our understanding of the cosmos deepens, we move ever closer to answering the age-old question: are we alone? Whether we discover microbial life on a distant moon, detect the chemical signatures of an alien atmosphere, or receive a signal from a distant civilization, the implications will be profound, forever changing our place in the universe. Until that day comes, the search continues, driven by our innate curiosity and the hope that somewhere out there, life has taken hold. But if intelligent life exists elsewhere in the universe, what might it look like? The most iconic image of an alien, popularized by countless science fiction movies, is the Gray, a humanoid figure with large black eyes, a bulbous head, and slender, childlike bodies. This image has become so ingrained in our collective consciousness that it's often the first thing that comes to mind when people think of aliens. But why has this particular form taken such a hold on our imagination? The answer lies in a combination of cultural and psychological factors. The gray alien archetype first gained prominence in the mid-20th century, notably through the alleged encounters described by individuals like Betty and Barney Hill. The Greys represented a blend of the familiar and the unfamiliar, Their humanoid form made them relatable, yet their exaggerated features added an element of the uncanny. However, this image is only one of many possible representations of extraterrestrial life. In truth, the potential diversity of alien appearances is as vast as the universe itself. To speculate on what aliens might look like, we must first consider the principles of biology and evolution. Life on Earth has evolved under specific conditions: gravity, atmospheric composition, temperature, and available resources. These factors have shaped every living organism, from the simplest bacteria to the most complex animals. If alien life exists, it would have evolved under different conditions, leading to potentially vastly different forms. For instance, consider the role of gravity. On a planet with stronger gravity, life forms might be shorter and stockier, with powerful muscles and thick bones to support their weight. Conversely, on a planet with weaker gravity, beings might be taller and more fragile, with elongated limbs and delicate structures. Atmospheric composition would also play a significant role in shaping alien physiology. Earth's oxygen-rich atmosphere has led to the development of aerobic respiration, but on a planet with a different atmosphere, life might rely on entirely different chemical processes. For example, in a methane-based environment, life forms could have silicon-based biochemistry instead of carbon-based, potentially leading to organisms that look more like living crystals than flesh and blood. The way aliens perceive their environment would also influence their appearance. On Earth, sight is a dominant sense for many species, but this is not a universal rule. In environments where light is scarce or non-existent, other senses might take precedence. For example, in the deep oceans of Earth, many creatures rely on sonar or electroreception to navigate and hunt, leading to vastly different sensory organs compared to land-dwelling animals. In a similar vein, alien species that evolved in environments where vision is less useful might have developed heightened senses of touch, smell, or hearing. They might possess elaborate antennae, sensitive to the faintest vibrations, or complex olfactory structures, capable of detecting minute chemical changes in the air. Moreover, alien species could have sensory organs completely unfamiliar to us, such as the ability to detect magnetic fields, infrared radiation, or even the passage of time. These senses would not only shape their behavior, but also their physical forms, leading to beings that might be completely unrecognizable as living creatures by human standards. The development of intelligence and technology is another factor that could dramatically influence the appearance of alien beings. On Earth, humans have evolved a large brain relative to our body size, leading to our distinctive skull shape. If intelligence is a common trait among advanced extraterrestrial species, they too might have developed large brains, but the form this takes could be very different. For instance, on a planet where energy is scarce, evolution might favor beings with smaller, more efficient brains, relying on collective intelligence or hive mind structures rather than individual cognition. In addition, in environments where technology plays a central role in survival, alien beings might have integrated machinery into their bodies, leading to cybernetic organisms that blur the line between biology and technology. Furthermore, the way aliens interact with their environment could lead to unique physical adaptations. Species that have developed advanced technology might have evolved to prioritize dexterity, leading to multiple limbs or specialized appendages for manipulating tools. Alternatively, a species that has integrated artificial intelligence into their biology might have neural interfaces or other forms of direct brain-computer connections. Just as human cultures have shaped the appearance and behavior of different societies, alien cultures would also influence the appearance of their species. Cultural practices, such as body modification, clothing, or grooming, could lead to a wide variety of appearances within a single alien species. For instance, a species that values symmetry might develop elaborate rituals to enhance or emphasize symmetrical features, leading to a society where individuals have artificially modified bodies that reflect cultural ideals. Additionally, the environment in which a species evolved would play a critical role in shaping its appearance. On a planet with extreme temperatures, for instance, life forms might develop thick, insulating layers or specialized cooling systems. In underwater environments, creatures might have streamlined bodies and fins, while those on land might develop limbs suited for climbing, burrowing, or running. Another intriguing aspect to consider is how alien psychology might influence their appearance. If a species has a different psychological makeup from humans, it could lead to physical forms that reflect those differences. For example, a species that evolved to be highly social might have features that emphasize communication, such as large, expressive eyes, complex facial muscles, or even bioluminescent patterns used for signaling. Conversely, a species that evolved in a solitary or hostile environment might have a more intimidating appearance, with features designed for defense or aggression, such as sharp claws, spines, or tough armored skin. These physical traits would not only reflect their evolutionary history, but also their psychological tendencies, leading to beings that are as much a product of their minds as their bodies. Beyond biology, the role of artificial life. In addition to biological life, we must also consider the possibility of artificial life forms. If a civilization has advanced to the point where it can create life, either through genetic engineering or artificial intelligence, the appearance of these beings could be anything imaginable. These life forms might be designed for specific tasks or environments, leading to a wide variety of forms that reflect their intended functions. For example, a species that has colonized multiple planets might create different forms of artificial life for each environment, leading to a vast diversity of appearances within a single civilization. These beings could range from tiny, insect-like robots designed for precision tasks to massive, tank-like creatures built for heavy labor or defense. Additionally, the concept of virtual beings must be considered. In a highly advanced civilization, individuals might choose to exist in digital form, abandoning physical bodies altogether. These virtual beings could take on any appearance they desire, further expanding the possibilities of what alien life might look like. Despite all these possibilities, it's important to recognize the limitations of human imagination. Our understanding of biology, physics, and technology is based on our experiences on Earth, and while we can speculate on what alien life might look like, the reality could be far stranger and more complex than anything we can conceive. For example, some scientists have proposed the existence of life forms based on completely different principles from those on Earth, such as beings made of dark matter or life that exists in higher dimensions. These concepts are difficult to visualize, but they remind us that the universe is vast and filled with possibilities beyond our current understanding. In the end, the question of what aliens look like is as much a reflection of our curiosity and imagination as it is of scientific inquiry. While we may never know the true appearance of extraterrestrial beings, the exploration of this question challenges us to expand our understanding of life and the universe, pushing the boundaries of what we consider possible. The appearance of aliens, should they exist, is likely to be as varied and diverse as the environments they inhabit. Influenced by factors ranging from gravity and atmospheric composition to culture, technology, and psychology, the possibilities are nearly endless. While our imagination often gravitates toward the familiar, humanoid forms with slight variations, the true diversity of life in the universe is likely far beyond anything we can currently conceive. As we continue to explore the cosmos, both through telescopes and perhaps one day through direct contact, our understanding of what it means to be alive and intelligent will undoubtedly evolve. In the meantime, the question of what aliens look like remains one of the most tantalizing mysteries of our time, a mystery that invites us to look beyond the familiar and into the vast unknown. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.